So, hi everyone. Thank you for your time today and welcome to our webinar series here today. So today we will be presenting on component sizing and subsystems integration in a full vehicle context as part of our electrification series. Prior to actually kicking off the webinar itself, just a couple of housekeeping items for all of you. First and foremost, this is going to be an interactive webinar where we will have short polling questions throughout. So we look forward to your input and participation. In addition, if you have any questions as we're going through the presentation material, please don't hesitate to ask them in the questions feature in GoToWebinar, and we will aim to address them either by the end of the webinar or throughout, or we will email you afterwards. Do also note that this presentation material will be shared by email, and we will also be providing a recording for anyone who would have missed it or would like to review the presented material. In terms of quick introductions, my name is Daniel Mazar, and I will be your host for this webinar. I'm responsible for customer success and sales operations at Maya HTT. I'll introduce Maya shortly. However, from my point of view, in terms of the role that I'm currently doing, I leverage my electrical engineering background in supporting clients across North America on their complex engineering and digitalization strategies and challenges. And I'm very happy to be here with you. In addition, the majority of the presentation and technical deep dive will be done by my colleague, Anthony Lorella. Anthony is our senior technical pre-sales engineer responsible for model-based systems engineering. He's a specialist in this domain and has worked with multiple tools in relation to it and has been able to solve complex challenges in relation to MBSE throughout a plethora of industries. Vehicle electrification is one I've seen him have extensive hands-on experience with, and you're in really good hands today as for someone who's going to bring us through the majority of the presentation. So if we go next, I wanted to very quickly go ahead and introduce Maya HTT. So Maya Heat Transfer Technologies is the organization that's hosting this webinar, and Anthony and I both work for. Maya is a leading provider of digital engineering solutions and the #1 global partner for Siemens Digital Industry Software. Our organization has a rich history in digitalization tools. We did start in aerospace, though we've branched out and solved some pretty complex challenges throughout many industries over the last 3 years. In particular, I'd say in the last 2 to 3 years, we've seen immense growth around adoption of tools and really the challenges that we're seeing in vehicle electrification with having clients being able to handle and address cutting edge problems all across the world. So if we go next, this is just for those that may be joining us for the first time here, but if we're talking about Maya, today we're really touching on a small subset of what we do, which is in relation to simulation, but there's a lot of different spokes to the wheel where not only do we cover simulation, but if there's challenges in relation to design, going into manufacturing, even if we're looking at data analytics or applied AI, which is most definitely a great area of growth, there's a lot of different domain-specific expertise that we have in-house and that we can bring. So we pride ourselves on that strong engineering and technical background. And really, if anything here catches your eye or you want to have more information on things outside of what we're planning on presenting today, please don't hesitate to send us a note and we'll aim to address that. So with that, if we jump to the next slide, again, really today we're looking at component sizing, system simulation, and subsystems integration in a full vehicle context. There's some specific things we're aiming to cover here with you today. In relation to that, really we're going to look at building a complete vehicle system from different possible subsystems and really talk about sizing and integration of components. This will all be done in a full vehicle context, though Anthony will also be sharing with us more specifics there. We'll also talk about incorporating and reusing simulation data from the subsystem level as it relates to the complete vehicle systems architecture. So we're excited to have this presentation for you. With that, I'm going to pass it over to Anthony, who's going to take us away. Go ahead, Anthony, all yours.
Thank you, Dan. And hello, everybody. So yes, I'll also repeat welcome to today's session. Thanks for joining. We're really excited to have you here. As Dan mentioned, our focus today is going to be on system simulation. Again, I'll be taking you through the technical portion of the webinar, And let's just briefly go over here some of the contents of what we will be kind of addressing today. So the main things we'll be discussing are why use system simulation for hybrid and electric vehicles. We're going to look at that in terms of a deep dive into the tools we have and how they work, specifically as they relate to electric and hybrid vehicles. We'll be kind of focusing in there by breaking down the workflow and how it might vary across different types of vehicle architectures, and how we handle both the modeling and the analysis of these EVs. We're going to look at first, as Dan mentioned, a very high-level view of building a vehicle architecture, but then we'll start to kind of pick apart different subsystems and see how the tool can tackle those too. And finally, we're going to close out with how to extend, capabilities of this tool by leveraging information that might come from other tools within our portfolio of simulation, specifically regarding 3D CAE. So we'll plan to cover the integration of data coming from eMag simulation, so for the electric machines, and also how to have interaction with CFD for the fluid domain and different kinds of cooling applications. So first things first, we'll get started with our primary topic, why use system simulation and specifically SimCenter AIMSIM for the design and analysis of electric and hybrid vehicles. So SimCenter AIMSIM is our focal point for this, and we'll start with an introduction to system simulation as we accomplish it within our tool set. Specifically, this is our portion of our portfolio that specializes in system simulation. So this can include, 1D analysis of mechatronic systems and their controls. However, I will comment at this point, 1D system analysis might be a little bit of a reductive term. That terminology actually refers to the breaking down of the lumped parameter approach by which we model systems. 1D, the dimension that is common between all these systems is time. And so it does actually end up being possible to build a more complex, let's say 2D and 3D system. So just bear that in mind as we go through some of these examples. And the first thing we should cover is what is mechatronic system simulation. Now it goes by a lot of different names, as you can even see here. Sometimes we'll say just system simulation. Sometimes we can refer to mechatronics. I'd say all three. But depending on who you speak to, they might use a different word. It all means the same thing. And at this point, actually, what I'd like to do is maybe we can start with our first question to get a sense of everybody's familiarity with system simulation. So if we could actually bring up the first poll question for everybody, if possible.
Great. Just one
and I will
second,
do that
Anthony.
now. Oh.
I'm on it. Great. All right. So as Anthony mentioned, the first polling question should now be on your screens. Please go ahead and answer to the best of your ability. Again, we're just trying to gauge audience interest to make sure we're tailoring the content appropriately. So are you currently leveraging system simulation in your workflow? Pretty straightforward as per the definitions Anthony shared. Yes, no, or I'm not sure. So we'll give you another 15 seconds or so if you could just quickly let us know, and then we'll be able to move on. If you're not sure, or if you'd like a bit more clarification, please don't hesitate to put in a question or message us on the chat app, and we'll respond or address appropriately.
Mm-hmm. Absolutely. Thank you, Dan.
Great. With that, I think we're ready to start closing off the poll. Great. So for the essence of time, we'll start moving forward here, but essentially we saw a pretty even split in attendance from a yes, no, or a not sure perspective I think there's a slight skew towards people not leveraging system simulation or mechatronic system sim. But again, we're seeing a good distribution here, Anthony, of people on all sides of that. So with that,
Certainly
pass it back to you to continue on.
Thank you, Dan. So great. For those of you who are not familiar with it or aren't sure, hope this will be informative for you. And for those of you who do and are already familiar with it, you'll probably come out of here learning something new or that you didn't know before. So regardless of your answer, we'll have something for everybody here. But let's start with the fundamentals. What is mechatronic system simulation? So to answer this question, we'll probably need to develop a little bit of background into the approach behind system simulation and then expand on how we use AimSim specifically to do this. So here we'll use an illustrative example, which is the steering system that is pictured to the right. If we want to design that given steering system, there's probably a few questions we'll be asking at the onset of this design process. Things like, is the electric motor powerful enough? What can we expect in terms of time response of the system? For the hydraulics, what kinds of pressures will we reach? And are they predicted? Is there a risk of vibration? How do we integrate controls into the system? And you'll probably be familiar with some of these questions that are common across different kinds of design processes, regardless of what you're building. Even if it's not these exact questions, the idea is that the questions you're asking at this point are multi-physics and dynamic, right? And so what is required here is some kind of representation of your system so that we can get an idea of how it's behaving. Typically, we can refer to this as a plant model. And the usual approach to doing this early on is to break the subsystem up into individual components, usually represented by their physics, and then build a plant model in this way. And AimSim here, the way we approach system simulation is no different. We do the same thing. Where we do differ is actually right around here, where we differ from some approaches. Now, normally with this process, what you're doing is actually taking these physical domains, and for every one, you'll have analytical representations at the equations level, right, to represent the different physics. We are very much doing the same thing, but where AimSim actually builds on this is by using those equations level representations of the physics and wrapping them into graphical icons to represent individual elements of that domain, right? So for example, in the mechanical system, we have icons to represent things like a mass, a translational mass, or a spring and damper, or just a spring or just a damper. The idea is that that's what the user is manipulating, but on the back end, when we build a system, what's happening is the dynamic time-dependent equations are being manipulated on the back end to build the full system. And so the end result is that the user doesn't need to spend a lot of time rewriting proven theoretical equations for the different physics. Those are readily available to the user, and a lot more time is spent building up the system architecture, manipulating that architecture, doing performance analysis. The equivalent equations, by the way, are available for multiple different physics, whether that's electrical, hydraulic, as well as many others. So now we can see here the difference that I'll cover. The main differences here versus a block diagram approach are really the different graphical icons that we use. Normally, with a library-based approach, the end result is a much more readable and physically significant system that is very easy to determine, at a first glance, what's contained in there. Additionally, the libraries use a more multi-port approach, which means multiple variables can be exchanged between components, both back and forth. And this leads to a cleaner, more physically relevant sketch. So we can see that across the equivalent models with a typical block diagram approach and our components using a multi-port approach. Additionally, this leads to the different libraries that use this approach and how we can reuse them. And so those icons that we showed earlier, typically referred to also as components, can span multiple libraries representing a wide range of physics, many of which are listed here across several disciplines. So fluids, thermal, energy, controls, mechanics, engines, engine components, and electrical components. Altogether, these libraries house across all of them about 5,000 different components that allow us to build really any type of system. Additionally, these components are validated by the development team, and the time-dependent equations of physics that are behind them are fully documented for the user to view and are completely transparent. So what can we do now that we know what's available to us? Well, very simply, we can build the multi-domain system using these compatible component libraries, using the modeling environment, which is very user-friendly and highly customizable. We can run efficient simulations, dynamic simulations to look at all of the results, conduct in-depth analysis, doing post-processing like creating spectral maps or performing fast Fourier transform, as well as, and something we'll see later, connecting to the CAE world, integration with third-party software or other tools for simulation. So the tool is it's a very, very useful approach, system simulation, both for rapidly synthesizing a model for simulation at the onset of a project, but also to be used as a platform or a springboard to be able to connect out to other simulations or other studies that are going on within the same project. This is kind of furthering the efforts to make different kinds of disciplines, not so much their own individual silos, but being able to inform other decisions throughout the design process. So this interconnected ability to communicate with other tools allows decisions made at one point to inform other ones, and vice versa. So, changing pace a little bit here, we'll move from the high-level description of some of these things more towards the applications for electric vehicles and hybrid electric vehicles, as I mentioned. So here, the various libraries can come together to build pretty much anything which we have already seen. In terms of EVs or HEVs, the same is also true. These libraries, and specifically the more automotive-related libraries, support modeling of any type of electric or hybrid vehicle, because the components can be arranged in any order to create a particular architecture or even a novel architecture that can be saved later into a user-defined library for reuse. So highly flexible and able to build any of these. On top of that, the models themselves can be used for a number of purposes. There's a number of engineering challenges that we can tackle via system simulation. Even if it is built at the onset of a project, you might imagine there's limited capabilities. But that changes because the models here can grow with a project. The more information becomes available, the more we can expand on the model, the more we can do with it. So the vehicle models, for example, once built, can be adapted to serve these purposes. Early on, things like architecture selection and pre-sizing of electric machines is possible. But later, we can also integrate things like cooling system analysis for electric devices, or optimizing plant subsystems and their controls, and even virtualizing some tests that would normally be physical. All of these things are possible within the tool, and across the different libraries, this is what we can accomplish. So actually what we'll do is maybe pose the question to the crowd again to see where the particular interests or tasks associated with design lie with you. So we could pull up the second question here.
Great. I am on it, Anthony. Thank you. So speaking of those domains and subsystems, you should now be seeing the second polling question. Which subsystems are most critical for you? And we have three options. If you have any outside of the options, please feel free to share it in the comments with us. But
Please
which
do.
subsystem is most critical? Motor, battery, thermal / cooling. Of course, there may be some linkages there as well. So just use your best guess. Again, it's just to give us an idea as to if we need to shift a little bit of our focus here. So we'll give it another 10 seconds or so before wrapping this one up and passing it back. Anthony, while people are filling it out, which one would you say you see as the most critical in your interactions with clients?
Yes, so I think typically where people go to system simulation, as we'll see, usually ends up being, to a degree, a bit of everything. But the main question that comes up is typically the thermal applications. Because we can combine all of these different components together in one platform, we now have a very, very quick way to get an assessment of the thermal load. So that is an area where a lot of people have interest, because the sooner we can identify that, the more capability you have in terms of influencing your design.
It's a great point, Anthony, and I'll let the audience know that didn't actually skew the poll, since all the answers have come in right before, but that's exactly what we saw in the poll as well, with the majority of attendees filling it out saying that thermal and cooling is really the most critical system that they look at. We did have the second chunk talking about the motor and the smallest on the battery, so there may be some addressing those, but really the majority goes back to thermal cooling subsystems and related complexities. So with that, Anthony, I'll pass it back to you.
Okay. And I guess a comment there, as Dan, you mentioned at the beginning of the poll here, there is, the motors, batteries, and the cooling systems are highly interlinked. It's rare that you won't necessarily be concerned with motor thermal behavior. But the idea here is that we'll see in due time how we can tackle all of these things separately and together in a vehicle context. So now we'll start to dive a bit deeper into the tool, and specifically the approach that we have for modeling, building, and simulating all kinds of hybrid and electric vehicles that we just previously looked at. Right. So here we'll turn our attention to, instead of the high-level, let's say, philosophy behind system simulation, the actual modeling process within the tool. So the first workflow we're going to examine is the process of defining the vehicle architecture and defining the overall performance of said architecture, right? The idea here is that that's kind of a very early thing. One of the earliest things you'd like to do is get a quick idea of the overall performance, so that you can make architecture selection with actual, hard data to inform that choice. Especially at a point where you want to do it much more quickly than prototyping. You want to be able to, using system simulation, answer a lot of those questions, let's say in a virtual context or a digital context, to evaluate that architecture. So beyond developing those extended libraries of components, we also have a large amount of applications and custom UIs based around specific activities, many of which are actually applied to the development of different electric vehicle architectures. The aim here is to take processes that are usually very standardized in terms of early architecture sizing and analysis, and make that more automated for the user in terms of making that more easy. So things like identifying an undersized powertrain, and then being able to use something like a pre-sized motor tool to be able to quickly assess the powertrain performance. Beyond this, we have very, very simple workflows that are even more automated. So for example, the tool in question that we'd like to highlight today is something called the Hybrid Optimization Tool, or HOT. Now, what is this? It automates the development of an electric vehicle model, and it takes that process down to a matter of minutes. Instead of being able to having to really program a lot of these different architectures yourself, we've automated that process and have created a virtual assistant that allows you to build that model. So essentially, it's allowing users, either experienced ones or even new ones, to quickly develop a vehicle model with all the necessary components to nail down the architecture, and also incorporating that vehicle against the driver model and against the specific drive cycle. So it also, within our tool, we also have a list of standard drive cycles like WLTC and NEDC that can be used for the development or the validation of the vehicle architecture that you're to synthesize. It makes it very simple to kind of do efficient testing against various conditions, whether that's the drive cycle specifically, the conditions like battery state of charge, motor load, and driver response. So let's move on here to an actual application of this. What we're going to see is the hybrid optimization tool actually being used in practice. So here I'll take a second to describe what's actually going on the screen. Here we've got the UI of SimCenter AimSim. This is our system simulation tool. So what we can see here is the actual simulation area. And you can see in the very onset of the analysis, we are placing what is the hybrid optimization tool into the sketching environment. And normally this is where we would build a full system. But here what we're actually doing is placing the single component called the hybrid optimization tool into the sketching environment. And that's going to be normally, we would build a full system. But as we mentioned, what we're showing here is how simple it is and how easily we've automated that process. So all that's needed is that one little icon, and that allows us to get started. So the user will place that icon, and actually embedded within there is a script that's been created to launch a virtual assistant that helps in the development of this model. So here you can see that we are developing the different hybrid architectures already from the get-go. We have a number of vehicle architectures to choose from a conventional vehicle to hybrid to full electric or dual electric. Anything here is selectable, and we'll actually change the basis for the architecture. Here we're going to go with the basic electric vehicle architecture, and you can see it highlights the components that are involved in that process. Moving forward, we can switch sequentially now through these different steps of the hybrid optimization tool. We go from architecture definition to the architecture parameters. Now we've locked in the vehicle architecture, and we can start to define the parameters of those different components. For example, here we click on the battery, and you can see by clicking on the battery that there are a number of predefined parameters to define how that battery operates. From pack architecture, number of elements in series, branches in parallel, and then other other data like the minimum state of charge or the maximum voltage and minimum voltage. But if you look more closely, you can also see tabs that are related to defining the open circuit voltage and internal resistance. Whoops, that was jumped ahead a little bit there. Yeah, as I mentioned, for the open circuit voltage for a single cell and the internal resistance for a single cell. So we're able to easily define these here. Additionally, we can have the same type of parameterization for the motor. By clicking on the motor, now we're looking at bringing in tabulated data for maximum, minimum torque, and then also peak torque and losses. These by default are against things like motor speed. And you'll see that once we've at least gone over the data and made modifications to it, the component will now show up in green in our architecture, which means we've had a chance, it knows that we've looked over the data, and it validates that. These are default values. We're able to bring in anything we want ourselves and even kind of copy paste data from an Excel spreadsheet or a CSV if you have it. Moving on from here, we can define other components like gear ratios across them, and also here we're defining with the final component the actual vehicle itself. Things like tire dimensions, wheelbase, total vehicle mass are all being defined here to really characterize the vehicle itself. Finally, we're skipping here the transmission shifting strategy because it's not relevant to the architecture we've developed, and we'll move on to defining the test case. This is where we talk about the drive cycle that I had mentioned. By default, we're able to input a time versus speed target drive cycle, and we can preview it on the right in a graph. We can also change things like altitude and the electrical consumers as a function of time. But in this case, we're just going to keep the default drive cycle. But if you wanted to change it, you can change it to pretty much anything you wanted. Or alternatively, by clicking down at the bottom, there's a button that says predefined. And here we would be able to define, go through the list of predefined drive cycles. So here's where we would input it. And if you click on that, you can see that's our database of all the different drive cycles, which does get updated regularly. You can see that we clicked on a different one and it updated the graph for the speed target. The last step here is to actually compute the architecture against the drive cycle and see if there is any issues that come up. In the case there, it flashed a warning that told us actually it looks like over the course of the drive cycle you defined, the motor is not able to reach the maximum requested torque, and that's something you should look into. Although it is still able to build the vehicle model, it's just telling us before we even generate the sketch that it looks like the motor is undersized. So even before we get to the end result, we're able to make assessments on the drive cycle. Finally, we can post-process some of these values and look at what they look like. For example, we can plot a graph of time and speed, and to see what that looks like, we can look at displacement over time. We can look at things like state of charge as well if we wanted to. But once we're happy with that, you can see that we hit the generate sketch button, and automatically on the back end, that sketch is being produced. And there's finally just one last step here that we have to take the driver component and actually just simply combine it with the rest of the vehicle model here. And once that's snapped into place, all of the system is completed and we have a full vehicle model. You can see here what that looks like. So all of the different components are already in place: battery, motor, driver, also the control unit, and the vehicle. All of them are interconnected automatically, and we can click on any one of them and go back to assess those parameters that we had already previously defined. If you wanted to modify any of them, that's fully doable now as well. So we've got a defined vehicle architecture that we can now perform studies on and make changes as necessary. So in a nutshell, that is the hybrid optimization tool meant to facilitate the development of different vehicle models and different vehicle architectures and really make that process very quick to develop something against which you can start to do trade-off analysis, system sizing, all those different types of things very early on. But one thing I will mention is now that we've developed a vehicle model like that, it's not necessarily our end goal. We might be interested in doing all of those things, but typically once we have the vehicle model, that's only the start of the process. And the same is true with the model that we've developed here with our optimization tool. That vehicle model is a high-level representation. Although very useful, we can build on it and add complexity as we grow, right? So for example, we can add detail to the electric powertrain, as we've mentioned. For example, the motor model that we produced in there is just a foundation on which we can expand and add detail, and the same is true for batteries and other subsystems as well. And the idea here is that we can flesh them out using those components we saw earlier, more specific libraries, like thermal, electrical, thermal, fluid-related libraries. So in the image here, we can see that our initial design, the motor was not powerful enough for the given speed command of the drive cycle. So the other thing is we have baked-in capabilities for optimization within the tool. So it becomes very easy to resize that powertrain according to the requirements so that we get a better response to the design drive cycle. So as I mentioned, we have detailed libraries for modeling of electric machines that can be used to produce a more complex and a more dynamic model of the motor itself, taking into account the motor type, different kinds of losses, different parameters, and even things like stator compliance and the effect on the driveline. Additionally, there's dedicated components for motor torque or current control that can be used, and models of things like inverters add a lot of depth to the electrical portion of the vehicle that we didn't necessarily have earlier. So again, these dedicated libraries allow us to add detail to the electrical components and to be able to produce ultimately a more effective motor model, and also as a result, a vehicle model. Shortly after this, we'll be discussing how we kind of further expand on the motor model by leveraging more finite element data. So the other thing we mentioned is the link between the different components and the thermal aspect. Most components in the vehicle here have a thermal portion to calculate heat rejection based on parameters like efficiency. This makes it very simple to integrate thermal dynamics into the vehicle model by adding heat exchanges to the different electrical equipment, with our thermal library, and this contains all the necessary physical phenomena like conduction, convection, radiation, and different variations of those to be able to really capture the dynamic temperature evolution of different components. So in the example we have here, we can see that we modeled the temperature rise based on dynamic switching losses of the inverter behavior. And that's something we're able to do. And one thing I'll mention is, we can do this from a more standalone approach. So we can build a standalone model of these inverters and do a separate analysis of just those. And then when we're ready, we can integrate them into a larger vehicle context. But the idea is that many components in here have those thermal computations where we can compute heat rejection. And so they all can combine together to look at the total heat load of the different consumers on the vehicle. beyond just the thermal analysis for electrical components like inverters, we have dedicated libraries for thermal fluids and databases for both single-phase and two-phase applications. So this allows the users to build anything from a cooling system like a chiller plate against which we can actually cool the battery, or a refrigerant circuit, and even a cabin thermal analysis for doing something like a pull down or pull up test. And again, if we're able to quickly develop the vehicle architecture, it means we can that much more quickly integrate the thermal portion and quickly generate, again, with efficiency, something like a very, very high level pull down test or pull up test to validate that architecture or to validate the sizing of the different components. Additionally, we can expand on the detailed motor models with electric vehicle powertrain control. And I mentioned that we have torque and motor control that allows us to communicate with the motor based on the driver commands. So we can, for example, validate drive control with the vehicle supervisor in the loop. So this allows us to leverage a detailed library of other kinds of motor models. Multiple different kinds of electric machines, both synchronous and others, are available within those libraries, as well as more generic tabulated machines that are more agnostic of the actual technology used. Finally, one place we can go beyond the electrical portions actually on the driving dynamics themselves. We're able to also identify road conditions, road profiles, and look at the mechanics of the vehicle. So we can model the suspension system and a multi-degree of freedom vehicle body model itself, allowing us to assess things like personal suspension sizing, or the power steering system that we saw before, or even the vehicle braking strategies. We can do this for particular road profiles and different kinds of conditions, but this is something that we can also do in a vehicle context by developing the rest of the vehicle. So ultimately, the name of the game here is that once we have that vehicle platform, really we can go in any of these directions, right? We can go to the cooling portion, or we can then also use that platform to involve a chassis subsystem model, where we can take that and do a spectral plot. We can look at the order mapping for, like I said, FFE post-processing to look at an electric vehicle driveline. And this goes back to being able to do more detailed models, right? We can also develop individual models of just the electric drivetrain. We don't necessarily need to involve a full vehicle model, but we would have one at this point. Then the information that we get from a separate model like this can inform that one. So ultimately, there's a lot of different capabilities. The possibilities here are almost endless in terms of what kinds of models you can build or what kinds of different subsystems you can integrate in the vehicle context. But the idea here, generally speaking, is that you're able to do any or all of these with our dedicated workflows and libraries. All right, so again, we're going to progress here a little bit past just what can be done within the tool itself. Here, up until now, we've seen what our solutions for system simulation are capable of in terms of developing a vehicle model, looking at the performance of that vehicle model, as well as doing different kinds of analyses and what kinds of facilities we have within the tool to make this process simpler, more efficient, and clearer for the user. So the idea is that, ultimately we can easily build that vehicle model very early on in the design cycle, being able to make critical decisions with good information instead of very quick and dirty assumptions. We can now rely on more concrete assessments like our simulations, and ultimately come up with a more well-defined, fleshed out vehicle model. Once that's done, the question then becomes, what can we do with that vehicle model now that we've established it? So if you recall at the beginning of what I was discussing, we had that question of, you might have individual analyses being done by different departments, or the analyses are done in silos and never necessarily informing each other. So the idea here is that with the kinds of vehicle models that we're developing here, what is the capacity for one simulation result to influence or take information from and then be influenced by another simulation? So now we'll look at how we can integrate models and the results from these different models from other tools within our portfolio, specifically 3D CAE. So as we mentioned previously, that would be EMAG and CFD. We'll start with the information that can come from a simulation of our electric motor. Whoops. So there's a few points on the vehicle model that we can develop. So you'll see here, first of all, a vehicle architecture that is similar to the one that we had seen is developed with the hybrid optimization tool. The only difference here is that we've created, or we've used a more detailed motor model from the dedicated library, and we've used a more detailed battery model from the battery library. They operate much in the same way, but basically it's a direct transplant from one component to the other, simply that these are more detailed in the results that we can extract. You'll see also that we have the ability to model auxiliary consumers model. The idea here is that this is a very simple vehicle model that's not too far removed from the one that we created within the hybrid optimization tool. The idea is that, let's say this is our completed vehicle architecture with some of the parameters that we wanted to define. And now we'll see how we can add detail to any specific areas in the vehicle model by leveraging other simulations that we might be doing elsewhere. In this case, there's two particular areas that we would be able to influence, and those are the motor and the battery. Both in different ways, but equally useful and equally informative. So let's start with the vehicle's motor, and we'll explore how we can leverage our previous simulations into this vehicle model. Essentially here, as we've seen in previous sessions, we have a very capable offering for design and simulation of electric machines, being able to do anything from thermal to the electromagnetic, 2D and 3D analysis. Those can extend into mechanical and vibroacoustics as well. But what we're interested in particular today is the integration in a vehicle model, right? So here you can see at the very bottom, very well, I would say, fleshed out system simulation model of an electric vehicle, with the vehicle itself, the electric powertrain, battery cooling, and other systems also being modeled. One of which would be the electric motor that's being used. Here we can have different configurations, ready to go, but as long as we have the right motor model, we can see that you're able to essentially characterize a more detailed electric drivetrain based on the approach that we're taking, right? So here we can get from our solutions different data for sizing and looking at the actual geometry of the electric machine, do very detailed analysis, and actually be able to take that detailed analysis and distill the critical points from that simulation and take the ones that will influence our system model of the motor and be able to actually distill those machine characteristics and export them into the system model, right? So what we'll see is an example of how to actually do this, go from conception of the electric machine to the analysis, to then extracting those results that interest us most, and being able to validate that in a vehicle context. It's important here to understand kind of why we would be motivated to do this. So the idea is that, thanks to the interaction between these two tools, we can validate the motor capabilities in a more physical environment. The idea is that you have a motor design on paper. In the one standalone simulation, it looks to behave as expected, but there are other concerns that you might be interested in that can only be answered in a full vehicle context. So interactions between the machine, inverters, like we said, if it's torque controlled, then how is it going to behave with a given vehicle with the torque control that we have in mind? Not to mention cooling. One of the more I would say easily addressed questions for which we would combine data like this. And we'll see that there's a number of different kinds of points of information that the imported data can take into account. Things like magnetic nonlinearity, iron losses, impact of saturation, and other things can be actually extracted from this motor model and used in the vehicle context. The other thing is being able to assess the controls. Well, here, if we've established the torque control and the vehicle parameters, and to a larger extent, the driver behavior, then we can kind of determine the reaction time of the system that we've developed. We can take into account the machine limitations, as we've mentioned. And if we have the nonlinear data from the machine itself, we have a much more, let's say, high fidelity motor to work with in our larger vehicle context. So beyond the controls, there's also cooling that we can consider. If we have the more fleshed out losses from the electric machine that are actually coming from our detailed simulation, then a more accurate assessment can be made of the heat rejection from this component and the necessary cooling. Again, one of the most important topics that we can touch on with the system simulation model is actually that cooling in question. Because we have everything in one place and all of them can be linked thermally, it becomes very easy for us to answer that question. All right, so from here, we're going to look at an example of how we can do this, specifically by validating a design early and then looking at that in a vehicle context. Essentially, the thing that enables us to really do this is the fact that all of these tools are on the same platform. Because the process that I might have described just a minute ago might sound complex. When you see it in practice, it actually is deceptively simple. We're going to show now in practice the process of conducting the analysis and exporting that data to the actual EV model in SimCenter AimSim, and you'll see for yourself actually how simple that process is. So here you can see an example of the template-based interface that automates the model setup, right? And we're looking at defining the different parameters for the components, the electric machine, and the layout of it. here we're easily defining rotor and stator geometry from editable templates. So these are template-based approach, but these are easily editable. Here we can automatically generate the winding with provisions for the drive, slot, wire sizing, and other layout parameters, essentially helping us create a very realistic motor analysis. Here we can look at the cooling system, which ends up getting specified right after we define the materials. So we can define thermal, electromagnetic, and magnetic materials, and then assign the materials based on the database. And then we can use the preset virtual experiments that we have to look at the performance against target performance. So here we're doing a standard test that allows us to look at cogning torque, back EMF for the specific motor in question. So it's also important to ensure that the motor meets the target peak torque demand and the torque speed operating envelope is within the associated efficiency for the motor. And then as well, for the specific drive cycle here, we can look at the temperature evolution of the motor. And we can look at the various temperatures for the different motor parts given the drive cycle in here and the motor itself, and then look at probing the 3D temperature field to quickly identify the hot spots in the motor. And here we can see these are the benefits of doing a more 3D analysis. After that, we can look at, for these higher temperatures, we can check the magnetization for given loads and essentially just confirm the reliability of our design. So we can look at the use of efficient use of core materials by probing the local magnetic fields at the full load. And then the analysis can easily be shared using a report that includes motor geometry, specifications, and performance analysis with other parameters. And here we can see that we're easily, once we're at this point, we have a established motor design, we have the analysis results, and it comes time to actually share those with Sim-Center Aimsim, or tools for system simulation. Here, it's a very simple process. We export the results, and by default, there's already a file type that's compatible with Sim-Center Aimsim. And so we just choose a directory to store the exported file, give it a name, and save it. So other than the standard workflow for defining the motor model, it's really a two-click process to take that data and export it in a file which is already compatible with our system model that we've developed. And that's the key here. There's no pre-processing and post-processing necessary. We take we do an analysis, and then we take the necessary data from the analysis, which is compatible with our system model, and we place it in there. A very straightforward process. And as I said, when you see it in practice, it really is much more simple to use. Now we can move over to the vehicle model here that you've seen. And you'll see that we have a motor here in question, and it becomes very simple to grab the losses files and their specific capabilities. Because on both sides, that file type is identified by the motor. And so the file that's created previously is read and expected by the motor in the system simulation model. And so those properties, the motor losses and complex nonlinear behavior is actually brought into the system model. And now we have all of the performance and characteristics of the more detailed motor model in our 1D system level. And we can look at that in a more detailed vehicle context. So ultimately, as it had showed, we're able to then assess the performance of the more detailed motor against the full vehicle. So things that can get updated are the performance, so in terms of torque and efficiency, but also the losses. And that's one of the things that is greatly benefited from this approach, is the detailed losses that we can extract from our 3D analysis. That can go into our system model here. Again, a very simple process when you look at it from end to end. It really is a question of a couple of clicks to extract data from the more detailed analysis for EMAG into our system model. So moving on, we're going to keep actually on the topic of integration with our 3D CAE tools. But now we're going to switch over to how we can leverage our simulation capabilities in CFD, specifically here for fluids and cooling. And if we recall the system model that we had identified earlier, here instead of the motor itself, here we can do a number of things with CFD in terms of battery cooling or different kinds of fluid modeling. But specifically, I will mention that we actually have a capability within the tool itself to have embedded CFD simulations. So if you have capabilities for doing CFD analysis within our SimCenter tools, well then we have an embedded tool that allows us to do that underhood cooling analysis. And what you can see here is we're able to develop a system model with different kinds of heat exchangers and actually assess them in 3D space. So we can look at a 3D stack of heat exchangers and define them in an XYZ plane. And within our system simulation tool alone, we're able to kind of combine that with the CFD solver and look at the underhood cooling of that heat exchanger stack. Again, this is done just like before with we saw with the hybrid optimization tool. This is done with a automated user interface. So this is a very first level kind of CFD analysis we can do that takes advantage of our solutions and actually embeds it into the tool. You can see that here. So we can define the geometric parameters, and then we have a dedicated interface to interact with our CFD solver. And then it will generate a very simple 3D geometry based on what you defined and look at the thermal behavior. And essentially, it's as it mentions it here, the idea is that this, what we call co-simulation, is happening as a result of the exchange of information, right? So if we are combining CFD and system simulation for thermal calculation or for a thermal cooling, one side will be able to compute air velocities and temperatures, and the other side, as a result, will compute the required, or not required, but the resultant heat release of different components. And so, temperature and heat flux are tightly coupled variables together, and in this case, that's how we are accomplishing this co-simulation. One half is assessing temperatures, and the other half is assessing heat release, informing the other one, and producing this co-simulation. So by combining these two capabilities together, we're able to quickly address things like underhood system architecture, being able to quickly define changes based on what we see as necessary or if we're lacking in certain areas. But the embedded CFD particularly allows us to really get into the more accurate results from defining that geometry. So, you know, when you start new vehicle programs, there's going to be several dozens of alternative configurations that you might be looking at in terms of different grill designs and heat exchanger arrangements. But when you're defining them, it's not going to be very long before you need to make a selection of the best few that needs to be done at that moment. And so CFD is particularly capable of making that assessment, at least in part, but when you combine it with the system simulation, you're able to get kind of a full picture of the different components interaction and the airflow. So this embedded solver allows us to take into account that CFD technology and bake it into essentially the 1D framework that we've been looking at. The main thing here to keep in mind is that we've facilitated this process as well by creating a step-by-step GUI that allows you to define the parameters and the domain, 3D fluid domain calculation, automatically mesh this, and then link it to the AIMSIM model. Again, just like we saw with the hybrid optimization tool, this process is very, very user-friendly and useful for you know, both new and experienced users. But beyond looking at what's capable in terms of an embedded solver, we have other capabilities to combine with our CFD tools as well. For example, if we look at a full vehicle model that we've been looking at previously, we might need to really ensure that we have accurate cooling across something like a battery pack. And what's beneficial here is that we can take that same approach of combining temperatures and heat fluxes to something like a detailed battery pack model that we see here. So the drive cycle and all the different components can be modeled, you know, in our system simulation, but the complex cooling, you know, whether it's a liquid cooled or air cooled, you know, flow paths can be modeled from a more detailed standpoint with the CFD tool, and we're able to pass that information back and forth. So essentially, we can see that for things like you know, fluid paths here. So if we have a vehicle model, we can take the heat flux from a component and send it off to evaluate what that battery pack temperature would look like. Or we can do the same with a motor and look at the complex cooling flow paths for the fluids. So you can see that each of these tools has their own strengths. Being able to determine more geometric, you know, spatially complex 3D simulation will give you more results in terms of temperature distributions and more detailed flow paths. But being able to do that for a specific subsystem or component that requires that complexity, and then handing that off to a more detailed vehicle model. The benefit here is that we aren't making assumptions in terms of boundary conditions, because the thing that's determining the boundary conditions for the 3D simulation is our system model. And so the two are linked together, they're coupled. And so those boundary conditions will change dynamically at regular intervals, and one simulation will inform the other. Here we'll look at just a last example of actually how that happens in question. It's a very simple process, but here we'll see the co-simulation. Essentially, we have a system that we've built in SimCenter AIMSIM, and in this case, not a electric vehicle, but just a simple hydraulic and mechanical system. And you can see really the star of the show here is that specific component called the TCP socket connection. And that allows us to connect via co-simulation, whether that's locally or over a network. But we're able to define the location for sharing the different variables. And you'll see that what we've defined are specific input and output variables. So how many inputs do we have? How many outputs do we have? The definition of that component in the system simulation model by default allows us to create the necessary files that are read by the CFD analysis. And so on the CFD side, all that's required is actually to toggle the co-simulation. And you can see one of the fields here is actually for co-simulation. If we click that, we can select SimCenter AimSim as the co-simulated tool. Once we click that, actually, we can define a couple of extra parameters, but the default ones are usually fine. And go on to just link the boundaries of the simulation to the imported variables that are coming from SimCenter AimSim. So here you can see we are able to detect, or we're defining the boundaries in the co-simulation here, and those are going to come from SimCenter AimSim. And here all we need to be able to do, it already knows via co-simulation that it's going to be expected to come from AimSim result file. And all we need to do is really define where that's coming from. And so we define the same port location and host location that's storing the results on the AimSim side. So that TCP socket, we just need to actually set the same connection port number and host name. And once those match, we can automatically identify the data that's coming from the AimSim tool. Once that's done, actually, the two are compatible, and we can launch the simulation from one tool and then complete it from the other. And then you can see once that's done, the two will run together. One will do a time step, and at regular intervals will pass boundaries back and forth across the other. So the idea is that you can have very detailed results, but embedded into a much more complex system model that has all the rest of the information associated with it. So that was our last example. Actually, before I wrap it up, I do want to ask the final question. Based on what we've seen today, we will go to our final poll question and get an idea of, of the different topics that we've covered, which ones are most critical, or which ones, do you deal with typically in your design process?
Great. Thank you, Anthony. A lot of excellent information and examples shared there. The poll itself should be in front of you now, everyone. So again, which part of the design process do you tackle? So we'd like to hear more specifically about your role in the work that you do. So it could be CAD, could be design, it could be a little later in terms of testing and prototyping. So,
and for elaboration purposes, we can lump simulation in with design.
Great point, Anthony. So again, you're doing CAD, you're doing sim and design, or testing and prototype. Just take another 10, 15 seconds and just go ahead and share that with us, and we'll move on towards wrapping up the presentation itself. Great. I think we're ready to move on. And okay, Anthony, just to let you know real quick, the large majority of attendants and people filled out are in that simulation and design category. So we don't really have a lot of representation in terms of testing, prototyping, or people doing CAD, which again, I think relates to sort of the audience of this series. So with that, Anthony, I'll pass it back to you.
Great. Thank you, Dan. And I think that result was somewhat expected, but it's always interesting to make sure that we understand which perspectives are represented here in these sessions, because there's a lot of different disciplines that are being touched on, particularly when we talk about the interoperability between these different tools. It becomes necessary to maybe communicate with people who are touching on different disciplines, the capabilities that are available, making sure that you're leveraging them so that you can get the full benefit. But with that said, that brings us kind of to the end of the session. Here, I believe we'll wrap it up with questions and answers. But before we get to that, I want to thank you for your attention, and maybe pass it over to Dan, who can field any questions that have been asked.
Exactly. Wonderful. And sincerely appreciate it. I think there's some phenomenal information and relevant examples being presented. So just a handful of questions here as we wrap up. Firstly, can you talk to software in the loop, hardware in the loop, or SIL, HIL applications? Can the software support this? Is it something you see tackled often? Could you speak to that a little bit?
Absolutely. So the tool is very capable. That's one thing that we didn't necessarily mention in detail, which is once I have a well fleshed out vehicle model, we can, beyond just modeling the subsystems, extend that into doing software or hardware in the loop analysis. We have a compatibility with a number of tools that allow us to do this, but we're easily able to import data, let's say, from other tools that allow us to develop controls, or AimSim is able to kind of produce and extract a real-time compatible vehicle model that you can place on a real-time platform.
Great, that definitely addresses that question. And another one for you, Anthony. You didn't touch as much on chassis systems. Could you talk about how the software would be able to simulate, let's say, chassis systems for vehicle dynamics?
Yeah, so I mentioned it very briefly that we can model different things like the suspension, things like that, but we have a dedicated library that I didn't cover in today's session, specifically for vehicle dynamics. That has a kind of different levels of detail for developing a vehicle model, like I said, with multiple degrees of freedom. But not only that, we're able to define in great detail a road profile. So up to and including importing a road from a tool like OpenStreetMap. So we can extract a road data from something like OpenStreetMap, embed it into our model, and actually create a virtual track that our vehicle can run on with realistic vehicle dynamics. In fact, it's so capable that we've actually created a driving simulator with a steering wheel input that allows our vehicle model to react to external user input and allows us to drive on a specific track in that case. So we're able to create very, very high fidelity vehicle dynamics that allow us to even create a driver in the loop vehicle simulator.
Perfect. Thanks, Anthony. And one final question. In terms of being able to design and simulate for control logic, could you talk about AimSim and its relation, or how would you interact, either simulate or working with another tool set controls logic? Could you speak to that?
Yes, absolutely. So when we talk about control logic, I think a de facto tool that comes up in the industry is Simulink, and that ends up being kind of the like I said, the default tool for accomplishing some of those things. And as a result, we've developed a very, very good interoperability with a tool like that. Well, with Simulink and tools like it. Essentially, it's a very simple extraction process, and it's bidirectional. We can either embed a vehicle plant model into into a Simulink model, so that we can combine the control logic with the vehicle model in the Simulink environment. Or we can take the S function that would come from Simulink, embed it into a SimCenter AimSim, and actually just define the outputs and inputs that we would need to communicate with the vehicle model in our platform. So it's a two-way street, and it works very well in both cases. And I would say, what's really nice there is that We're leveraging the capability of our system simulation for the designers and systems engineers. But that capability of combining with a tool like Simulink Controls means that that model gets to be reused by controls engineers who like to, who have developed a lot of capabilities in tools like Simulink and are able to reuse those and keep using them, but against the more fleshed out vehicle models that are being developed. So no efficiency is lost, no knowledge is lost by utilizing this in conjunction with the tool like Simulink.
Excellent. That was a great answer, Anthony. A lot of detail being shared there, and just talking about that bi-directional exchange. With that, we have reached the end of this webinar. Once again, great, and many thanks to Anthony for that wonderful presentation. Also, a big thank you to the audience for sticking around and going through it. As mentioned, the recorded material will be shared as well as this presentation. If you follow us, please let us know. If you recall, this is part of our overall vehicle electrification lunch and simulate series. Our first session spoke a little bit more about integrated electrical systems design. The second one was on electric motor and magnetization. This one is on systems, and the fourth and last one, which will be held same time next week, Tuesday, is based on your input. So we've got a number of suggestions and recommendations from the audience. You have one final chance to submit your recommendations by 5 p.m. Eastern today. Please email us on one of the earlier emails you've gotten, or send us a quick note. If there's anything specific you'd like us to cover, we will be making a decision and sending out a note tomorrow as to what will be included in that session. So we really look forward to seeing you in that last session. Again, the final session, its details, as well as all of this relevant material, will be made available to you by tomorrow. So sincerely appreciate your time. Wishing you the best for the rest of the day. Thank you once again for attending. Bye now.